So now I've exhausted all the Chinese I learned 10 years ago, but at least I finally got a chance to use it. So today I'm going to talk about static typing in Python. And sorry about the technical difficulties. It doesn't like full screen, so I'm going to be non-full screen, and you can ignore the icons at the bottom and all that. So some practical applications. So as was mentioned, I'm a lead developer of Cython, and Cython is it's hard to describe, but one of the ways to describe Cython is it's the easiest way to create C extensions in Python. And Cython is a language that interoperates with Python, and then it also interoperates with legacy libraries written in C, C++, Fortran, and so on. And then the other thing that's nice is you actually don't have to go and code your stuff in C if you want to make it fast. Cython allows you to actually write code that's really low level, down bare metal, and runs directly on the processor. So the way I like to describe Cython is you can map out languages in terms of their simplicity and performance. And so up on the upper left-hand side, you have Python. It's fairly simple to write, but the performance isn't always what you need it to be. Granted, probably 80% of your code does not even need to worry about performance, but sometimes you do. And then on the lower right-hand side, you have languages like C++ and Fortran. And the performance of these languages can be really good, but it takes an enormous amount of expertise and care and patience to wield these languages effectively. Very easy to shoot yourself in your foot, very hard to get working code. And even for an expert, lots of times it takes longer to get good working code in these high-performance languages than Python. And if you look at these differences, what are the reasons that you have simplicity versus performance? And one of the reasons is it has to do with things like memory management and things like error handling. And another really big thing is static typing. That's one of the differences between these languages. Well, enter Cython. So Cython kind of lives in this space between these two languages. If you can take your normal Python code and you can compile it with Cython, and it lives up in the upper left-hand quadrant of the Cython space. Or you can spend a lot of time manually managing your memory and using pointer arithmetic and all that clever stuff, and live down in the right-hand dangerous world just like C. And the really beautiful thing about Cython is, unlike this former environment where if you found your Python code wasn't fast enough, you had to take a flying leap off this island and jump all the way into C, and then somehow write a bridge between these two languages. With Cython, you can move your code gradually. So you can optimize just the portions of your code you care about. You can start with code that you know is correct in Python, and over time, as demands require, you can move your code around this entire space. It really is a continuum of a language in terms of simplicity versus performance trade-off. And one of the primary benefits, one of the primary things that gives you this trade-off is the addition of static types. So one way to think about Cython, probably the simplest way to think about Cython, is that it's Python with optional static typing. And by static typing, what I mean is that you can say, you know what, I have a variable x, and x is actually a C integer. And when I say C integer, I mean it's a C integer with the performance of a C integer and also all the defects of a C integer, like, say, wrapping around to some platform-independent upper bound. At the same time, I can say, well, you know, I have a couple of double numbers, A, B, and C. And the really nice thing about being able to say this is that 50 years have gone into making our modern processors crunch double numbers very, very fast. You can also have more complex types like integer pointers to spare all your eyeballs. I have not written a function pointer here, but you can do that in Cython. And this allows two very key important ingredients. One is that you can now interface with languages like C that require signatures of these types. So, for instance, if I want to call a C library, I can't just pass it a Python object and expect it to know what to do. But I can say, well, you know what, this function takes an integer and two doubles and returns a double. And if I declare it as such in Python, then Python will handle all the conversions from the object from Python to the C level, call the C library, and then get it back again. You can also then actually use these types to write your algorithms in Python syntax, in Python style, and it compiles down to C code, which is manipulating these raw types directly. So here's an example of something you might want to write in Python. This is a little hard to read there. It's the extended Gcd function. And it's a number theoretic thing that given two integers, it computes their GCD, the greatest common divisor, and then it also computes two cofactors such that A times P plus B times G equals this GCD. And by the Euclidean algorithm, you know that such a thing always exists. And here's a simple Python loop that will perform it for you. And you might say, this is all well and good, but it's just not fast enough for my purposes. I'm computing GCDs as part of a web service. Maybe I'm doing some crypto, and I really need to do 1 million of these a second instead of only 10,000 of these a second. And so with Cython, what you can do is you can say, well, let's type some stuff. So I say, OK, the Gcd function, it returns a long, and it takes 2 longs. And then let's type some intermediate variables. Cython does have a little bit of type inference, so these are not always necessary, but just for illustrative purposes. And then when I compile this function, what it will actually do is instead of these integers being wrapped in Python objects that are wrapping a C integer, they will actually literally be C integers. And this code will run 100, probably 200 times faster than the original Python code. Now, it should be noted that we have placed a couple restrictions here. For instance, whatever the long type is on your system, we now can't compute the GCD of anything bigger than a long. The other constraint we have is, say you have you're a mathematician and you are working with a decadent domain and you want to compute Euclidean algorithm on those. This now is restricting you to work exactly on integers. So there are some trade-offs here, but most of the time, say, if you know in your application you want to use integers and you want to do it really fast, this is a really nice trade-off. So you see, this is really easy to do. And there's this great temptation here to say, well, let's type all the things. And I've seen this happen time and time again, that every time I teach someone Cython, I say, OK, so Cython is really easy. You just add types. And then the second thing I have to teach them is, you don't actually add types everywhere. Please don't add types, even though you can. And for example, in the Sage Math project, right next to the xGCD function, there's this great xKCD function. And it's a little bit different. It takes a single integer, and it returns you the kth xKCD comic. And you say, well, you know what? I want this function to go really fast because I'm calling this a lot. And so I'm going to use Cython. And I'm going to type my things. And I'm going to say they're strings and files and all that kind of stuff. And actually, if you look at this code and you run it, it doesn't go any faster. And you spent all your work actually making a Cython file. You actually restricted it. You say the input can be a string only. No integers allowed anymore. And it might actually run a little bit slower because it's doing type checking. So an important thing to know about Cython is you really only want to add types where you need them. You don't want to add types everywhere. So types are tools. And they're tools that be leveraged by a developer for a specific objective. With Cython, we usually have 2 objectives. One objective is performance. We type our things because we want them to be fast. We know what the types are, and we don't have to figure out every time in every single iteration of the loop for the interpreter to have to say, OK, let me look at this variable and figure out exactly what type it is again, and dispatch to the right algorithm for doing addition of C integers. The other objective we have in Cython is we want to interface with C code. And types let us do that by saying, this library produces these functions with these signatures, and we want to call them. And so Cython will automatically do the conversion, but it needs the types to know what kind of conversion to do. So this is a little bit about Cython. And so I did Cython when I was in grad school, and I obviously still do Cython. But the time came, and I ended up graduating, and I got a real job in the real world, and I was spending my days coding in Java. And you might say, well, what is a Python guy like me doing coding in Java? And actually, it was a little bit better than this. The job I had looked more like this. I was working for Google. I was doing what it didn't have this name at the time, but now the name is called big data, not gigabytes of data, not terabytes of data. We were churning through petabytes of data. And this was just a really, really exciting opportunity. We've got lots of interesting challenges. We're working with amazing engineers to try to churn through the world's information. And the project I was working on is called Flume Java. And as you could guess, it's written in Java. So I spent my days coding in Java. And when I was working in Java, something really interesting happened. I'd come home and I'd be hacking away on Python. And every once in a while, I get this really weird feeling. And I said, if only I was coding in Java, I wouldn't have made this mistake. And it really hurt me. And I said, well, why is that? And don't worry, it didn't happen near as often as when I was in my day job and said, oh, gee, I wish I was coding in Python. This is so annoying. But it still happened occasionally that I'd be coding in Python and say, well, if I was coding in Java, this wouldn't happen. And I started to think to myself, well, really, what is the problem here? Python is such a great language. What is it missing every once in a while that makes me say, well, if I was coding in other languages, things would be better. And so I got to thinking about that. And one of the things that we programmers like to use is we have lots and lots of tools. One of the primary tools is IDEs, and there's a whole lot of IDEs that, out there. Us mere mortals don't usually use butterflies to code, but we use a lot of other tools. And whenever you have an IDE, you open it up and it's thinking about the code. And it's trying to make decisions for you. And it's trying to say, you know, is this a valid function call? Is this really a method on that object? It does things like completion. You know, you type period and it says, well, what are your possible options? What do you think you want to code next? And who calls this? A big purpose of IDEs or other tools is not when you're just looking at a piece of code. It turns out that you actually, one of the philosophies that Python gets right, is you spend a lot more time reading code than you spend writing code. And when you're looking at code, you're trying to get familiar and say, okay, who calls this? What context calls this? What is this illegal function? And to try to actually make sense of all these different things, the IDE does static analysis. So it looks at your code, it looks at the variables, it looks at the expressions you have, and tries to figure out what's going on. Now, in order to avoid solving the halting problem and causing undesirable side effects, it doesn't actually execute your code most of the time. So this is really a process that goes on that's static analysis. And in Python, your types are available at runtime. So you're really constrained. And maybe about, if you have a really good type inference engine, about half the time you can maybe place a good guess on what your types are. But that's not good enough. The other thing is that sometimes guessing what your types are is efficient. For instance, if you're looking at tab completion, you might say, well, you know, as long as it gives me a pretty good guess of what's out there, and then, you know, if it got things wrong, I can actually manually correct it, that's good enough. Well, sometimes you want to do more than just guessing. You want to actually use these tools to manipulate your code. If you're doing some refactoring and you say, you know what, I want to add an argument to this, a required argument to this function. And you want your tool to be able to say, you know, there's a default value of false, and go through my entire code base and add this argument everywhere. Well, now guessing isn't just good enough. You really have to know what the types are everywhere, to know where the call sites of your function are, to actually do this code manipulation. And another important factor is that this isn't just for IDEs. This kind of analysis is what we do in our head when we're looking at code. And probably our brains are the most important tool we have, and types let us know what's happening in the code. And usually when we're looking at a snippet of code, well, if you wrote it recently enough, you might know what all the types are supposed to be. But if someone else wrote it, or you wrote it a year ago, you might take some guessing. And something like static typing is documentation that is enforced. It's something that doesn't go out of date. You could add comments, but we all know that comments get out of date fairly frequently. So here we are, again, in the situation where our types are tools. The objective here is different than performance. The objective here is to be able to understand your code, to be able to reason about your code, and to be able to manipulate your code. So that's your objective here. And I also got to thinking, well, why, when I started hacking on Flume Java, did this become more important to me? Well, I think it has to do with code size and complexity. So here, for personal projects, you know, Python is my go-to language of choice. And you know, if I'm, I have a family website that I run. I have, scripts to do server administration, and these usually around, they cap out at a couple thousand lines of code, and you can kind of keep the whole thing in your head. Then you move on to bigger community projects. So IPython, interestingly enough, it used to be 4 times as big. I think the Jupyter Notebook split changed this. And Cython, they're decent-sized projects. They're not quite 100,000 lines of code, but it's small enough that you can kind of get your head around them, but they're big enough that, you can't see all of it at once. Then you get into your bigger projects, like Django and Sage. These are projects that are over 500,000 lines of code. They're to the point where no one has read every single line of code in this project. And to have a Python project this big requires a lot of discipline. It requires a lot of care, it requires conventions, it requires good comments, it requires an extensive amount of tests, and this is certainly feasible, but the overhead of manually managing this code becomes greater. And also, I should mention, the overhead of exploring and understanding this code becomes greater too. So, and then we have enterprises like Google. Now, Google has a lot of Python. This bar chart would go up through the roof and beyond, no doubt about it. And millions and millions of lines. It got to the point where you're jumping, and another great thing about Google is everyone can see all the source code and jump in and make changes. But if I want to understand what code does, when I'm just looking at the file, I want to be able to see who are the callers of this file. And there might be 10,000 callers of this file. There might be 3 callers of this file. I don't know. But without automated tools, there's no way I can manually comb through the code base and find them. And static types are one of the key features that allows you to have this giant index of your code that is navigable and manipulable in a way that you just can't have without your types. So as projects grow, this type of information becomes more and more important and more relevant to your job. So you think to yourself, well, wait, isn't dynamic typing one of the things that makes Python great? I mean, this is why we're not sitting there coding C and Java and all these other languages, because we don't have to worry about this stuff. Well, dynamic typing is one of the things that makes Python great. So enter this idea called gradual typing. So while I was working on Cython and promoting the idea of optional typing, fortunately for me, there was someone who was putting this on a theoretically sound basis. And there's actually a group of people. Jeremy Seek is one of the primary instigators of this. And he wanted to approach this notion of gradual typing. So on the one hand, you have static typing. And that's your traditional languages where you have to declare the type of every single variable every single time. And then on the other hand, you have something called dynamic typing. And this is still strongly typed, but the types are implicit and the types are at runtime. And this is something like Python. And the question he asked himself is there a way we can make this, instead of a binary choice, a continuum? And so we have some of our code is statically typed, some of our code is dynamically typed, and then when the two collide, we really want to do something sensible. We want to provide value to the user in this middle ground. And we want to provide value to the user incrementally as they move from the dynamic typing side to the static typing side, because they're putting effort in, and for every little bit of effort they put in, they should get a little bit of benefit. And so, so this is what he did. And actually, while I was getting ready to come for this conference, I was thinking about doing a whole talk on gradual typing. And it turned out that Guido scooped me at the last PyCon and gave this great talk on gradual typing, which I will not try to reproduce. So you should all go and watch that. But here's the basic idea. So there's this magic any type. And the any type is, it's a new type introduced into the system. And then the key feature is there's also this non-transitive consistency relationship. The any type is consistent with anything, and anything is consistent with any type. But the non-transitivity is key. That's what allows us to insert this any type into a traditional typed calculus without collapsing everything to a point. So typically, the any type sits at the very top of the type hierarchy, and it sits at the very bottom of the type hierarchy or type lattice. And if it were transitive, then this whole thing would collapse to a point, which makes it very easy to reason about and very unuseful to get any information about. So the other thing that he does is he says, okay, so now what we can do is we can take a program that's partially typed, and we just declare anything that is not typed by the user actually is of type any. And then if you don't type anything, everything is of type any, and you have dynamic typing, and everything works out fine. If you type everything, you're in the static typing. And the great thing is, now you can actually go along this continuum, and with this consistency model, you say, well, whenever two things intersect, if there's the any type, then it's legal. But if more and more stuff becomes static, the more and more stuff we can disallow because it's actually illegal, and will cause errors at runtime. So, and it should be noted that this doesn't mean you actually have to type everything. There's actually a lot of room for type inference where you can say, well, you know, I didn't declare the type, but my compiler, my tool, my analysis can figure out exactly what the type has to be, or what the set of types has to be, and can do more intelligent things than give it the any type. So this recently, just in the last year, has started to really gain traction in the Python community. And so there's two PEPs, there's PEP 483 and 484, that pretty much introduce this, this notion of, it gives a standard for doing gradual typing in Python. So there's this new typing module. There's the any type. There's also union types and iterable types and type variables and a whole bunch of stuff. It turns out that types are more complicated than just classes. But it gives a whole suite of operations that allows you to, maybe not completely, but fairly expressively annotate the types in your program. These type annotations, they're going to be put where Python 3 introduced the kind of empty space that was intended for type annotations, but at the time, no one knew what these type annotations should look like. Well, now there's a proposal. This is what type annotations should look like. The interesting thing is these types are still hints. So they're not going to be actually enforced by the Python C API runtime in any manner. But the nice thing is that people can write external validators to go over these types and to check things. People can write external IDEs that understand these types and reason with them. For instance, we have a great code search tool at Google, and we can use these types to actually go over our code and build indexes so you can navigate the code effectively. Another thing it provides is it provides standards for where you put these types. It provides a definition of stub files, which says that you can actually declare your types external from the program itself. If you have overloads and these other kind of corner cases that are really hard to describe, it says, okay, this is how we're going to do them. And now there's this standard that, that people can rally around and use. So the current focus of these PEPs is on this second use case. This is type safety. I want to understand my code, and eventually I want to manipulate the code. And this is a partial step forward for tools like Cython, but it doesn't actually address the problem completely. For instance, it doesn't have a very good way to type local variables. And in Cython, that's actually one of the things you want to have typed most of all, is your local variables are the things that are manipulated and touched inside your inner loops. And you know, that's where you spend all your time. So, and there's a couple other things that it doesn't quite address very well. But this actually is a huge step forward in terms of a standard for ways to define types, and hopefully, eventually, we're working to figure out how to best incorporate this into Cython. So this is really exciting. So you might get to the point where you say, you know what? I like types for performance, and I like types for correctness. Are there any use cases where I really need types for both of them? And this is something that's actually just come out quite recently in my job. So if you remember when I was talking about Flume Java, and I eventually had Flume C++, and I really, really had this itch. I said, well, you know, what would Flume Python look like? Because that's what I want to have. I want to have the beautiful system that we've built around Flume for doing big data processing, but I want to use the Python language to actually to implement my code. And so we just came out with this product at Google called Google Cloud Dataflow. And this is essentially just an externalization of the Flume project. As part of the Google Cloud platform, I was actually pleasantly surprised to see my colleagues here. So that's kind of fun. And what it looks like is this. So Google Cloud Platform, the Google Cloud Dataflow has two parts. So one of the parts is it's a model for doing large-scale data processing pipelines. So it's an SDK that allows you to express these pipelines in a very clean and succinct way. This has a lot of advantages. Instead of worrying about allocating machines and resources and all that kind of stuff, you just express the logic of your pipeline. You express the logic of your pipeline in the kind of application level. You don't have to worry about optimization and putting things the right way. Another nice thing we do is we unify the streaming and batch model. So traditionally big data has been batched, where you say, I want to fire off a nightly job, it processes all my daily logs. Well, now you say, well, what if I want to process those as they come in? Well, we've managed to unify those models in one SDK, and just you can flip a switch and do one or the other with the same code. The other half of the Cloud Dataflow is that it's a managed service for executing such pipelines. So notice I say it's a managed service. So we actually have different backends for the Cloud SDK. We have Spark backend, there's an Apache Flink backend of the works, and you could imagine a Hadoop backend and all these other backends. The SDK itself is open source. We explicitly wanted to be able to plug in, plug out runners. And then we also have this Cloud Dataflow service, which we think, you know, we're trying to make the best way to run your pipelines, but we don't want to lock you in. So this is kind of the lifetime of a pipeline. So up on the upper right-hand side, you write your code. You say, you know what, I want to take in data. I want to take in all the Twitter feeds, all the Twitter tweets that are going out, and I want to do some processing. I want to extract the hashtags, maybe build an index on those hashtags, figure out the most popular ones for the last hour, and then publish those to my website. So you write your logical pipeline, and then you submit it to a service. And what the service does is it looks at your pipeline, which is kind of this big, huge directed acyclic graph of steps that you want to run, and it says, okay, let's turn that into an executable plan. Let's do some optimization to it. So it does function composition, it does binary lifting, it does a whole bunch of different optimizations to try to figure out how to most efficiently execute your pipeline. And then it manages the workers. So it actually says, okay, well, you know what? Your data looks about this big. We're going to start up this many workers. And it starts up the workers and sends them work and you know, handles errors and tells you when you're done. And then we also have this monitoring API. And we have this huge service built up. And if you look closely, it's only this upper right-hand box where you care about the language. The whole rest of the service is language agnostic. So for better or for worse, Dataflow, the first offering of Dataflow, it came out in Java. And that's, there's a lot of reasons for that, but that's where we are. And we want to do something better than that. We want to do Dataflow in Python. So one of the differences between Java and Python, there's a lot of differences. One of them is the types. So if you look at the top, if you can't read that, the big takeaway here is the bulk of this code. This is a huge line of code. And we say, you know, we have a P collection, and we want to do a parallel do. A parallel do is just a map function where we say, element-wise, for every single input of my billion elements, I want to do this to it and then produce some output. And it is true that Java 8 adds lambdas, but that doesn't quite solve our problem here. It's implicit, it's not very clear in the source, but a lot of this design was done around the fact that typing in Java is very verbose. For instance, this process context is actually an inner class of the do fund, so that it inherits the do fund's type parameters. Originally, you'd say, well, why don't we pass the element we want to process in? Well, if we pass the element you want to process in, well, then you have to redeclare the type of the element. And Java doesn't have type defs, and I have literally seen code at Google where you have to say, okay, where do I line wrap this type declaration? Because it's more than 100 characters long. And you know, maybe it's actually like 4 lines because your type declaration actually is 389 characters long. And it gets really, really ugly. Contrast with the Python. This is, by the way, this is just provisional. This is our current API, but we're still tinkering with things to figure out the best way to express this. But we have one line. We say flat map, and since there's no types to worry about here, we can just have the logic itself. We say, you know, we're splitting this, and we take x and we do some regular expression to split it into pieces. So that makes me really happy. I'm saying, you know, with Python, we have this really, really great succinct API for writing exactly what I want to do, minus boilerplate. So let's take a look at another example. So side inputs. This is the idea of a broadcast variable. And this is where the types in Java that were palatable before now start to bite you. You say, okay, now we have to have this typed P collection view. What is a typed P collection view? Well, it's really just this object that you carry around to hold the type and to reference the type. And because in Python, we don't have to worry about, because the types are dynamic, we actually don't have to have a separate object to hold the type. And because the signatures are more flexible, we can just pass the type in as an ordinary argument. So on the bottom, you see, we say map, and we have a lambda that takes 2 arguments. One of them is the main input, the element, and the other one is this, this side input, we call it, which we want to pass everywhere. Much, much more succinct. Similar thing happens with side outputs. We've got a huge whole bunch of code that has to deal with, we create these tuple tags, and these tuple tags are, again, handles to be statically typed and statically correct. And on the bottom here, we have our very succinct Python version. Pre-join. This is like a join, except for when you're doing joins with big data, sometimes you don't actually want to take the full cross product, because even if you have the capacity to handle 1 trillion elements, no one has the capacity to handle 1 trillion times 1 trillion elements. So sometimes you want to be more intelligent than actually take the full cross product. And this whole thing is the Java version. Has a lot to do with creating these tuple tags that are just handles to carry around the types. And we have the Python version. And one of the things about the dynamic typing is our left-hand argument, our input to the join, can actually be an ordinary Python dictionary. And then the output to the join is actually dictionaries as well. It's very, very clean and very pretty. So one last example. Composite p-transform. So one of the benefits of the Dataflow API is we provide a couple of primitive operations, but most of the operations that we provide are actually composite. So our primitives are parallel do, this is the element-wise, and group by key, which is kind of the shuffle in Hadoop, if you know that terminology. So we have all these other operations, and really what there are is they're just composite operations made up out of smaller pieces. And you can build up whole libraries of these operations that are made up of other operations that are made up of other operations, just like you do with functions in normal Java. You have good encapsulation. So this is what it looks like in Java. And you notice a lot of this boilerplate is defining the types and redeclaring the types and redeclaring the types and redeclaring the types. And in Python, well, you know, half the succinctness is due to this nice thing that we can have decorators and really nice syntax like that. And the other half is really due to the fact that we don't have to declare our types 3 or 4 times in a row. We might want to declare our types once, but we don't have to declare them over and over again. So when we're developing this API, we have to ask ourselves, well, you know, this is really, really succinct. Do we throw away too much? And we had an exercise where we had a bunch of people try it out, and we're playing with it. And we realized that, you know what? Type errors are really bad. And they're even worse in Dataflow than in ordinary Python code. So it's one thing to be sitting in your console, and you have, you know, a little IPython prompt or something like that, and you get a type error, and you look in you understand your code, and you know, it's right there, and you get it instantly. It's another thing to have a service where you deploy it. And then you have something that says, oh, you know what? Shard 389 failed with this type error. Way out there on some random data element. And these are really, really painful to debug. And we have a couple ways to mitigate this. One of the things is Dataflow has built in the idea of being able to have good testing, good unit tests, so you can actually run your pipeline entirely locally, entirely in memory. But it still doesn't quite alleviate the pain of these type errors. The other reason that you really, really want types is there are deferred errors. So one of the interesting facts about the Dataflow model is you actually construct your entire pipeline. So you describe exactly what you want to do, and it's deferred. When you describe, you say you want to do a parallel do, it doesn't actually do the parallel do right then. When you say you want a group by key, it doesn't actually do your group by key right then. It kind of remembers what you want to do. And the reason it does that is because it wants to do whole pipeline execution, whole pipeline optimization, and then submit your entire job as a service and run it in the most efficient way possible. So the problem with that is that everything looks fine, and your entire program compiles, and your entire program runs until you hit this execute command. And the execute command is when your user code actually gets invoked. And that's the point where you get this obscure type error. And even worse, there's this optimized step in the middle. So you don't just get a type error in your code, you get this type error that's intermingled with, you know, the framework code and the setup code and some of the optimization code, and then you get your type error. And you have to scratch your head and say, okay, in step 1, what did I do in step 1 that caused this strange type error to pop out in step 3? And so there's a couple ways we're looking at mitigating this. We're looking at more interactive modes. We'd love to be able to have something like an IPython notebook. It's an area of active development. How do you go from the exploratory thing to the production code and make this a continuum? But that will solve our problem partly, but not completely. Then there's another reason that types are really, really valuable here. And that's that lots of times you have these boundary errors. So as I mentioned, we have these things called p-transforms. And p-transforms are the basic building blocks of a Dataflow pipeline, and you build them. And the interface of a p-transform is it takes an input and it produces an output. And you say, well, that's a simple enough signature. Well, the real interface of a p-transform is it takes an input of a certain type and produces an output of a certain type. And if you wire these things together, typically what you do is you say, okay, now I have all my p-transforms. I'm going to try them after each other. Say I'm importing an approximate quantiles transform from my friend down the hall, and I'm going to want to put that into my pipeline. And sometimes the types don't match. But if you don't know what the types are, it's really bad. And especially you can say, well, you know, what happened? I unit tested my code, and the natural thing is I unit tested my red box. That works. Unit tested my orange box. All is good. Unit tested my yellow box. 100% code coverage. And then I wire the things together, and how do I unit test the combination of these two? Well, you can do that, but it's just not as natural as unit testing units. And so, but if I had type hints, the key is the types are really an important part of the interface of this model. And the other thing that this breaks is if you don't have type hints, you have to actually look inside these boxes. It breaks the encapsulation notion. And you have to like say, okay, I look inside the box, and I look inside the box, and I look inside the boxes in those boxes to figure out what the actual concrete types are. And you really don't want to do that. If you're handed a library transform, you want to be able to say, I know how to use this, and all I have to understand is the interface this transform provides, not its implementation. And the interface really involves intrinsically what types does this thing accept, what types does this thing reject. And you want to get that error early and in a clear way rather than later on. So, as I mentioned, we want types for correctness. Performance is another thing. So we started out the talk with, in Cython, we add types for performance. And this is really because you want to be able to declare these things at a very low level to run them on the bare metal processor. Well, types are actually useful for performance for other reasons too. So in Dataflow, you have this notion of P collections. These are these values that sit between your operations. And you want to have a schema for a P collection. When you have a P collection, you want to be able to say, this is a P collection of ints. This is a P collection of records. This is a P collection of strings to represent Twitter tweets. And if you don't have a consistent schema, if you say this is a P collection of objects, of Python objects, then you have to resort to something like Python Pickling. And Python Pickling is great for sending little bits of data around, but by the time you send large bits of data around, you really don't want to use Python Pickling. It's fairly expensive in terms of CPU, but it's also very expensive in terms of size. For instance, whenever you pickle an object, it puts the fully qualified name of that object into the pickled string. And then it pickles all the fields by putting their fully qualified names in the string. And you might say, well, let's see. Maybe we could do something very, very, very clever and label we could just say we have one schema, and then everything that breaks the schema will handle differently, but most of the time it will handle the same schema. That actually breaks with the one place that we materialize this data, which is in the shuffle operation. So you really have to put these, if you don't have a consistent schema, you have to put the schema on every single record and to shuffle it around, because you're really sending elements from machines to other machines. So typing is really important here. So now we have a use case where I want types. I really want types for my Dataflow API. I want them for correctness, and I want them for performance. And I want types everywhere. One thing to note is hopefully the type inference means that I don't actually have to have them everywhere. But I want them in a lot of places, enough that the type inference can figure out all the rest of the places. So again, we come back to this idea. The types are tools. And sometimes we really want them. And we want to leverage them for specific objectives. So this boils down to the question of, well, I hope by now I've convinced you that static typing is good. But we're all here at PyCon, and one of the things is we believe that dynamic typing is good. And Jeremy Seek actually has this great blog post about this, and he says, well, what's the problem here? And the problem is that both of these are right. Static typing is good, and dynamic typing is good, and it really doesn't make sense to talk about either or. You really want to have both. And there are different cases where you want them, and so the takeaway from this talk is let's enjoy the benefits of static typing in Python some of the time. So thank you. So any questions?
When would you determine what is a good time for static or when a good time for dynamic typing?
Yeah, so I think the way to decide when it's a good time to have static types is to look at yourself and you say, why am I adding types here? And say, I'm adding types here for this specific benefit, then, and then it, of course, is a cost-benefit trade-off, but you don't want to add types unless you know what you're trying to achieve.
Are you using this static typing for reduce errors, like the type error, or uses to improve performance, like Cython? And one more question is that when you're using this static typing, you're using the PEP4A3, PEP4A4, or like Van Guido said that he wants to take the static typing into the future Python.
Yeah, so I think typing is important for both performance and for correctness. And in terms of the question about the syntax of 483, 484, I think the syntax is not actually expressive enough to say everything we want, especially for Cython. But I think it's a really important standard to kind of put a stake in the ground and say, here is a huge number of use cases that we can cover with the syntax, and we can all importantly agree on a syntax to define types and to reason about types and where to put your types. And so I think it's a big step forward there, even though it's probably not far enough. And actually, even the PEPs say this is provisional. We're going to try this out and tweak it, as we find necessary. Because it's really hard to do something like this without having real-world experience to know what the best thing is.
Okay, thank you. It's very interesting. Do you have any code example that Python using type to show us?
Code example. So I have, there was the Cython example. So this is the Cython example of using types. The PEP, I actually don't have code example of the PEP itself, but let me just bring this up if you have not seen this. So this is right here, an example of types in the PEP. So here it just says that the name is of type string and the return value is of type string.
It looks like a little bit like Swift.
Yeah. And actually this is, this colon and arrow notation has been in a lot of languages. We're not the first ones to introduce this. So, yeah. It gets more complicated when one has like any types and unions of iterables and stuff like that, but yeah. Yeah.
Hello. As you mentioned, you said the dynamic type language got boundary error. And is there any unit test guideline or framework that can mitigate this problem to ensure the type problem not be exposed?
So what one can do is, like, one can have unit tests and then medium-sized tests and then integration tests that actually run, say, the entire job as a complete mock of your external, production jobs. And this can catch errors like that, although not all of them. So I think one of the benefits of typing, as well as it being painful to write these tests, is these tests are usually not very efficient. And so lots of times people don't write them, and then you get your errors when you're in production. And you're actually, say, serving web pages, and a quarter of your web pages don't serve because of some type error that you didn't see. So the advantage of static types is you can actually get those really, really quick. Before you even try to run your code, you can see what the error is. So, and actually, I want to follow up on the type annotations. One of the key points of these annotations is type declarations in the Python PEP are all valid Python expressions. So there's no like new syntax or anything like that. You can have, like for instance, with generics, you have list, and then you do a square bracket, and you put, the type of the item in. But there's no new syntax there, so that's really nice.
So thank Robert very much. So let's give him a big hand.